Good afternoon, everyone. So today I'm going to talk about the technology we are developing at RaayonNova, which is smart contact lens with an embedded display enabled for AR and VR experience. And to start off, I'd like to throw at you a very basic idea, benign on one hand and very fundamental and critical on the other hand. Idea expressed by one of the greatest philosophers of all time, Arthur Schopenhauer. Everyone takes the limits of his own vision for the limits of the world. This idea underlies everything that we do with AR and VR domain. It's equally relevant to AR, VR headsets, smart glasses, and smart contact lens. The world, as we know, is created by our mind based on 5 senses, and the most influential sense that we have is the sense of sight. According to some psychologists, it contributes up to 80% of our knowledge base. So if we plug into that informational channel and provide additional contextually relevant information to the user of smart contact lens, obviously we stand to benefit greatly. All right, and that brings me to the mission of RaayonNova and our goal of building smart contact lens enabled for AR, VR that can hopefully eventually replace headsets like Microsoft HoloLens, Magic Leap, and so on. And we do believe that this is probably going to be the final frontier for AR, VR applications. Now, to build a fully functional and operational smart contact lens capable of AR and VR applications, executing these applications, we need to achieve several milestones. One is we need to embed display, that's obvious. Display needs to project imagery onto the retina of our eye in focus. Now the image display needs to be refocusable and accommodatable. And I'm going to spend some time today talking about this particular issue. And we have to have a way to control smart contact lens. So if your eye components are displayed on or superimposed on, let's say, semi-transparent display built into the contact lens, how do you control the system? How do you select your eye components? Mouse is probably out of the scope. No joystick, no haptics, no touching. You're not going to be touching your eye with your fingers. How do you control such a system? So we have our own solution that we believe is going to be the solution for smart contact lens as AR platform. Now, what has been done till now? A number of companies are playing around with embedding pixels into the contact lens. I believe Google started first. Google embedded first pixel under the auspices of Professor Babak Parviz. And then they started growing number of pixels, and other players kicked in as well. Universities are experimenting with this as well. So there is one big issue with on-the-eye display that had to be surmounted, and the issue is that naturally human ocular system cannot accommodate, cannot focus on an object which is closer than 7 to 10 centimeters away from the eye. And obviously, if you have display on your eye, we have a problem, right? So children can focus, I believe, on up to 7 centimeters. And as we grow older, our ability to focus on an object which is close to the eye degrades significantly. So once we reach 40, 45, we cannot focus on an object which is closer than 10 centimeters, right? Google came out with a solution, which is a workable solution, and it's called Fresnel microlens. Fresnel microlens is a refractive optical component that actually allows you to focus ray of light directly into the retina. So you can imagine array of LED lights built into the contact lens, overlaid with an array of Fresnel microlens. And the array of Fresnel microlenses is going to generate collimated beams of light hitting retina directly, and that imagery is going to come in focus as if the display is a few meters away. So that's the Virocable. It's a good solution, and there are a number of players that are playing around with this idea, and we think that this is going to be the solution going forward. Now, once we achieve a fully functional embedded display on a contact lens, we need to make sure that we can accommodate and refocus in different parts of an image superimposed on display. Right? Why is this a problem? So I'm going to explain what the problem is. Naturally, when we read a book or we look at an image, we move our eyes, right, with peripheral view. We have peripheral view and we have focused view. The entire field of view is divided into two sections, right? The focused view at the center of our vision, which is up to 2 degrees of visual angle, very limiting in humans. The rest, up to 120 degrees of visual angle, is peripheral view. So with peripheral view, we only see contour, some color, shapes. But once we register with peripheral view interest in some part of an image, we will accommodate or move the vector of the gaze of an eye to that part of an image so that the light reflected from that part of an image, or text, or whatever it is, object, hits our eye directly under direct angle, and therefore we will see it in focus and we'll be able to recognize digest this information. And visual cortex, our brain's GPU, will be able to stitch together a sequence of these focused images into totality of our perception. So, again, to fully recognize an object or an image which is stationary, we move our eyes sequentially, right, to accommodate and to learn what that part of an image is. Now, if we have a display which is built into contact lens, we superimpose an image on a contact lens, and contact lens is a priori spatially locked into position with the eye, right? If you try to accommodate, the display is going to move and the image is going to move, so you will never accommodate. So just to demonstrate as an example, if I have a rectangular display built into the contact lens, and in my peripheral view I will see a timer somewhere here, right? So I don't see the time, but I know there is a time, right? There's a timer and there's a timestamp that constantly gets updated. Now, it's on my eye, right? I want to accommodate to take a look at what the time is. I will move my eye. As I move my eye, contact lens moves, display built into contact lens moves, and image therefore goes here. I change vector of my gaze, to this location, right? And timer appears to be here. So how do I accommodate? So this is a fundamental problem that has to be solved in order for smart contact lens to be usable as a platform for AR, VR experience, right? And at RaayonNova, we do have a solution to this problem. And what we propose is that we shift responsibility of bringing parts of an image into focus from the eyes to the display. Well, what does it mean, right? What does it mean? It means that the image needs to shift in a diametrically opposing direction on display to the attempted accommodation. So, what we need to do is we need to detect change of focus of the eye from external plane, because if this is, let's say we are talking about just AR, augmented reality application, that means that we are going to be dealing with transparency, semi-transparent display of some kind, built into contact lens. So normally we would be looking past that display at objects external to us. To look up something embedded display, part of the image that is overlaid, we'll need to change focus, and then we'll need to accommodate, meaning we'll need to shift vector of the gaze, our eyes will move. Change of focus is going to be detectable event, and we need to track it, and then we need to track change of vector of the gaze. Right? We need to constantly monitor where our eyes move. So the combination of the two will allow us to track attempted accommodation and correlate it to the disposition of an image in display. And I'm going to demonstrate it with the following example. So you have figure 5, right? It's the left upper corner. 501, this is the contact lens. 502 is hypothetical rectangular display. 503 is the dashed line, which is the center of display, area of display that comes in focus. The rest is going to be peripheral view, which is out of focus. Right? And then you have figures, okay, running ahead of myself. So, in figure 5, this is the pristine initial view. Right? The user wearing this contact lens has in upper left corner temperature indicator, timer, upper right corner, and below in peripheral view at the bottom of display, there is a running news line that is constantly updatable. Right? And the user looks through the lens at external object. So if you look at the fat arrow 504, it indicates the point of interest detected by the smart contact lens system, a point of interest of the user as attempted accommodation. So in order to detect that, what had to happen is the user had to change focus and start moving his eyes to the left upper corner in an attempted accommodation, right? So what the system does in response to this attempted accommodation, the system recomputes disposition of an image overlaid on display so that the temperature indicator comes in focus at, we're looking at figure 6, at the center of display, right? So 603 is the focused portion of the image that retina sees in focus and can clearly recognize that part of an image. So temperature comes in focus at the center of display. Next step, 604, the system detects interest, next interest of the user. User wants to read running news line, right? So the entire image goes up. The system recomputes disposition of the image on display so that news line, running news line, is shown at the center of display at figure 7. So unless we implement the system that can accommodate this, we cannot have a truly AR, VR capable smart contact lens, and we believe that this is the solution going forward. We do differentiate between two types of frames of references. In this case, this example is two-dimensional frame of reference, where image is depicted on display or superimposed on display, rather, with respect to two-dimensional geometry, X and Y, of display. There is also three-dimensional, which I don't have an example for, but the idea is basically the image needs to be superimposed with respect to external geometry. Let's say you're running Microsoft HoloLens and you are executing Amazon Prime, you're running movie, right? You can, with your hand, attach that application to the wall, it'll stand that wall regardless of how you move your eyes or your head. So this is a three-dimensional frame of reference, but the basic idea is pretty much the same. Now, I'd like to jump, in the interest of time, to SCL system of control. that we are proposing, right? This technology relies on the method I described just now, and it builds on it. So imagine your smart contact lens executes, let's say, Windows operating system. You have a bunch of UI components, some of which are selectable, and triggerable. Right, so normally by using selectable and triggerable UI components, we control different aspects of our system. So let me again run through an example. Figure 11 should be familiar to you at this point. Smart contact lens embedded 1102 embedded rectangular display, and in peripheral view you have 2 radio buttons, 1 checkbox, and 2 triggerable buttons, approve and deny. So this is the starting point, figure 11, right? 1104 shows the point of interest of the user. The system detects attempted accommodation, again by tracking focus and by tracking vector changes in the gaze. The image, disposition of an image gets recomputed so that the checkbox, which is of interest to the user, comes in focus at 1203 in figure 12, and due to the fact that the user has selected that particular UI component and focused on it, the UI component gets selected. Perhaps because the user keeps focus for 1.5 seconds or some time frame that is indicative of his choice. And the system selects it, so there is a check, right? Simply by selecting this particular UI component. And then 1204 shows us a next point of interest of the user, which is approve button. So the user wants to approve his selection. He did a checkbox, whatever that might mean for the system, for this particular application. And the next thing he wants to do is approve. Right, so there is an attempted accommodation, again, to approve button. Apparently user, without changing his focus, will bring down his eyes in an attempt to accommodate to that button. The system is going to recompute the disposition and display of all UI components, the entire image, and approve button is going to come in focus at figure 12 at the center of display. Right, and because we just we selected that particular UI component, which is a button, we brought it into focus. We pre-selected. So sometimes in Windows, sometimes you can trigger immediately. Sometimes you can select and then trigger. Right, as 2 different steps. So you can select. And if you're holding your breath and focus on that button for another second or 2, you actually trigger it. A triggering event is generated in Windows, and application-specific functionality kicks in and something happens. You're probably getting charged a few dollars on a credit card if you're approving a payment, whatever it is. So, we also, in our patent pending application, we also allow the triggering action to be an external action, like, for example, a double blink or clap of your hands, or perhaps voice command or something else. But basically, it's mostly eye-based control system. How I'm doing on time? So just quickly, oops, hold on, I want to come back. My apologies, I just wanted to run through one specific example. It's taking time to remind this. Did I lose anybody? Does it make sense? Questions, comments? Anybody? So this is it's probably not the best example for what I wanted to demonstrate, but still. So imagine that at 1403, this is an image capture sensor, right? That could be a CMOS sensor, perhaps. And 1402 is our embedded display. Now imagine that this display shows you three buttons: record, or play, or pause, or stop, maybe four buttons, right? If this is video camera-like arrangement. So by looking up at record, accommodating to record button as UI component, you can actually initiate a function in the system so that image capture device starts processing imagery and possibly recording it on internal memory or transmitting elsewhere. That's the idea. Again, everything that you do is happening only with your eye, through attempted accommodation. I think this is it. Questions? Comments?
At the beginning, you've shown us all the most important milestones. When you think, is there like a general timeline, do you think you will achieve them? Like, is it more than 5 years or?
Timeline?
Yeah, like general. Of course, I don't expect you to tell me that it's going to happen in 2 years.
You know, it's difficult to project it. If you asked me 3 years ago, I would probably say, I would have said that it's probably 15 to 20 years ago, away. A functional contact like this, contact lens. Now, given the level of miniaturization achievable, right, and the 2D printing that is happening, you can actually 2D print something like this, or close to this. Now, not with the best materials, right, it's not going to be fully functional, but it's getting much closer, and the time to achieve this is increasing. The speed with which we can achieve it is increasing constantly. So now, to me, it looks like we are probably 3 years away from it.
Thank you.
All right. Thank you very much.